So, from the as we said, we mentioned that we initially started the course with Fourier series. Then from Fourier series we started with Fourier transforms, and this Fourier transform, we call this one FT. This was a domain which this was a transformation which makes possible to go from some real domain, from real numbers, to complex domain. Today, we're just going to see some examples how we can manipulate data which are mostly in 1D. Now, when we say 1D, one dimension, actually we just mean data that we can plot them in a graph. Y is a function of x. Okay, so this is, or a data that can be expressed as a vector. Okay. So we start with this type of data. In the future lectures, we're going to discuss also what the Fourier transform can contribute when we have data sets which are of 2 dimensions. And in fact, they can even be implemented in 3 dimensions, even if we have 3-dimensional data. This is also possible. We can take the Fourier transform of 3D data, and we can obtain important information where probably from the first week class material, we mentioned the example of how the Fourier transform of 3D information, which is in the bones in our body, using computational tomography, we can print out all this three-dimensional information about the internal structure into an outer surface. Okay, so in principle, those are Fourier transforms of this 3-dimensional data set, which is, for example, if someone wants to see what somebody has in the lungs or in the brain, that's what we do. And this ability to extract this information attached on a tape, so you can think this one as if you are writing down the information on a piece of paper on the outer diameter of where you are going to take the data in a scanner, which you take this, traditionally you take the scanner in a hospital. So we're not going to go here. We're going to start today only with some examples of what we do in 1-dimensional domain. 2D could be images. That's the best example that we can provide for 2-dimensional data. And 2-dimensional data, we define this one 2D because we are going to have here T1 and T2. Okay, this makes a data 2-dimensional. Or similarly, we can have here X and Y. So this is a 2-dimensional data because we can allocate a specific readout at every location X and Y. Whereas here we have a function Y, which is a function of time. Okay, so they are not dependent. Just that we are just in 1D data, it's like a signal. A signal is a function of time. This is what it is. And this is what we are going to see today. In principle, what we can often do with the Fourier transform, it would be the following. Let's assume for a moment that we have the data set in the real domain. The data set in the real domain, we can denote it as U, okay? Or let's assume that the x-axis is we have time, okay? And from time, we have a function U, which is a function of time. If we take the Fourier transform, if we go to this new domain, we get a new axis, which is a k space, and together with this k space, we can obtain ut. Okay. With ut, let's consider this one as Fourier transform of u. So this will be equal to, actually, let me use this part of the board. So in the real domain, which was the best way to write, so let's do it like. No, I think this is good. So we go this way just by applying ft. So here we see that ut is equal to the Fourier transform of a signal u. This is what we can denote here. Then we can, in this real domain, we can add plus a function n, which is noise, and we can get un, okay, a signal with noise. And similarly, now this un we can take the Fourier transform, we can go this way, and we can get the UNT. So this UNT would be the signal with noise, then Fourier transform. So we can write this one here as UNT would be equal to the Fourier transform of UN. And as we're doing this, we can assume that we have the initial data here, the data with noise here, and then here we get also the Fourier transform of this one, and this is the Fourier transform of this data, where the noise is added in the real domain. But what can happen is that here we can add also noise, which would be of the type n plus ni. Okay, so we can add also the noise in this domain, and traditionally, let's say, the noise here, it can be represented as random numbers, okay, 1 to 10. If we say random numbers 1 to 10, this would be the noise in real domain. But if we write down random numbers 1 to 10 plus a complex number, which is times random numbers, so this is random numbers 1 to 10, this is the noise that we have in the Fourier domain, because these random numbers will have both a real value and a complex value. So we are adding something which has an amplitude for sure, but it has also a phase. Okay, para cada fase, cada amplitude. Or even what I want to say is that this noise in the real domain would be this one, the noise in the complex domain would be this noise. And then what we can follow different paths in terms of trying to explain the data. So it might be good actually to draw a schema like this, and you can always consider that we can follow this path from the function u. We can go to ut. We can add noise here, okay, and then we get UNT. From UNT, we can come backwards with inverse Fourier transform, and then what we can do here in this domain, we can remove the noise, okay. So we can remove the noise in this domain. Actually, let's assume that we have a function which is n inverse, which is inverse of the noise. Here, similarly, we can also have n inverse. So let's think again. We can take a function, take the Fourier transform. This has no noise, okay? We add the noise here. This becomes a noisy signal. And in fact, if we add the noise here, probably it's better if we denote this one as ut, which is the Fourier transform of this one with noise. And utn is different from unt, because UNT it has followed this path. The signal, you add noise, it becomes UN. You take the Fourier transform, it becomes UNT. And then here, in this domain, we can apply noise inverse functions. So let's denote this one as n inverse. Let me write this a little better. So this is noise inverse. We can apply this in this domain. And once we apply this noise inverse, we can go from UNT, we can obtain, let's say, just UT. So from here, employing this noise inverse function, we can come here, and then what we get a signal which is filtered out, which has no noise in complex domain, and we can come back and forth, okay? So whenever we want to see how we implement these, it might be good to think of a schema that might look like this. Now, go into our screen. Now these codes, I shared these with you also in the Google Classroom. You can also download and test with those. I think last time we implemented this part where we use the Fourier transform, how to obtain the derivative of a specific function. Now, the use of finding the derivative of a specific function using Fourier transform, it can be beneficial because FFT is a very fast, the computational complexity, it is improved a lot because it's using the fast Fourier transform algorithm. And that could be, that is one use, indirect use of why we use the Fourier transform to get the derivative of a function. And this is the example we covered the last time. And let's see now what we have here. I thought, I'm trying to find which could be the next. Okay, we can start here, December 4th, 2020. So when we talk about the noise or in the real domain or in the complex domain, the main concept is that noise is white noise, which means that it is random and it has all the frequencies inside. So white noise, this would be the same principle like in white light, which is composed of all the colors from red to blue and even much more components. If we add all of those together, we get the white light or the light of the sun, which we see outside. And for a moment, let's assume that second. So here we get 50 measurements, and we generate also a vector which is composed only of zeros. Where is this average? So this is the vector that we can see it here as which is full of zeros. And then from here, what we want to do is that sorry, give me just 1 second. Hello, it's me. Oh, mute. Jam l'élection, pardon. E përdorim, po desha edhe me qesat, edhe po, janë të E311, të këto kati 3. Okay. Falem. Kemi kolegë që ka problem në makinën. Okay, vazhdojmë atëherë. Okay, so it looks like we set a certain number of measurements, and what we can do here is that apparently we can generate a random number. So let's see what this can produce. This is just a shift F7. These shortcuts here, they never work. So here we observe just random numbers which have a specific amplitude, and this is the vector A, and we keep adding the same noise over again and again within this for loop, and we can observe actually what we see in the end. Okay, so this is how we are averaging the noise. If we notice the y-axis, it keeps decreasing, and this is from 0 to 17. Okay. What? What was this? This is 0 to 70, 0 to 3. Is this how we can do this? I just want to see how we write this, the limits in the plotting of the graph. Wait a second, this is... Okay, I want to see this. Apparently x and y, they're just written like this. Okay, no commas. I did a mistake then. Okay, so yes, the noise is getting lost, maybe. Okay. Now, this example, this might be pretty common sense because we're just adding frequencies which are, since the noise has positive and negative values, they're going to cancel out the previous signal, and it will be like a destructive interference. We'll start this again. Oh, okay, so apparently this was all going on. Finally, okay, so anyway, so it looks like we start with this huge signal, but averaging out, this is how we start and remove the noise. Now let's see here another example, and in this example, we have, apparently, we can generate a signal which has 30 units of length in one axis. So this could be x, this could also be time. We are not assigning any value right now. But once we do this domain or this complete range of 30 units, let's call it in time, we assign also 512 data points over which we're going to discretize the time axis. Now, if this will be the number of data points in the time axis, we have to do something similar also for the k-axis. Now, this k-axis is in the complex domain, or we can call this one in the frequency domain or Fourier domain. And so by now, here we have generated the value of k, so the x values for the k space, and the value for t. So t is somewhere in here, so t2, actually t1, so t2 is just generating all the data points from -15 to +15, because the complete range is 30. So we go from -15 to +15. And then similarly, but in the end, we get n+1 data points. We need to remove one of those because we need to have 512. And then we generate also the k, and then we define a function which looks like a Gaussian. Okay, so this is like a good-looking function. So this is, here we have the u, and this u, we evaluate the selection, and our function is going to look something like this. We could plot this a little grid on, and then I think we wrote this, a k, it was defined before. Let's evaluate this again. And then, so we have the u. The u, in a similar way like what we wrote on the board, is this function, which looks like a Gaussian, like a normal distribution. It's in the real domain. What we do is that we can immediately get this signal and transform this one and get the Fourier transform representation, which is the signal with no noise, okay? And if we try to plot this here, we can find that we have plotted the initial signal in the real domain, which is going to look like here. Then we can plot the other component, which is going to be actually the Fourier transform of this signal. And we can, wait a second, so this is second 2t. So this is the Fourier transform, and the width of this function, it is inverse proportional with the width of the first one in the real domain. So these two functions that are the first and the second one, this is how they are related with respect to each other. But now what we can do is the following. So we could immediately take the Fourier transform, inverse Fourier transform of this second graph, and we can obtain the initial signal, the first one. So from the second one here, I don't have a way to, so let me make a hand here, no. Okay, so wherever this hand is moving around, if we take the inverse Fourier transform of this signal, we can get this. But we can modify this a little bit by assigning some values of the Fourier transform by putting them 0, okay? So ut, let's see, ut is a Fourier domain, and let's zero out manually a few terms, okay? And actually, it might, before we do that, let's see what ut is. Let's print it here, and it looks like the initial values, because there are 512 of these. Wait a second, okay. We have a little more, we have quite a few, okay. So the initial values is like 53, 50, 43, minus 35, and so on. So with these initial values, we can actually, let's just change only the values of u1. Let's make the very first value of the function in the Fourier domain, let's make this 0. So we zero this manually. If we zero this manually, we've changed just one value, which is ut, and then let's try, once we do this ut, let's generate u real, okay? U real is now, let's evaluate this, is now, it should be, since we are taking this u real as inverse Fourier transform of this second function here, we should be getting something similar to what this first graph in here. But let's see what we get. Okay, we get a function which has deviated slightly from the very first one. So if you compare the first graph here and the third one, it looks like the third one, it has an amplitude less than 1, and also the amplitude here at the extrema points is just, it's a little below 0. So the first graph and the third one, they are not the same. Why? I think we clarified this one, because we said that the very first value of u, we just manually set it as 0. So we changed a little bit this function in the Fourier domain. We can change also a second value, evaluate selection, and then we can plot here figure 5, evaluate selection here, figure 5. Okay, so this has changed much more. So in principle, the first, in this subplot figure, the first one, the third one, and this new one, they are the same functions, just that figure 5 has been modified by changing only 2 data points out of 512. We can change one more. Evaluate the selection. Let's do this figure 6. So we just want to show actually the figure 6. Okay, let's see how much this can change between 5 and 6. Okay, so we didn't see much. Wait a second, they seem to be very similar. Let's change once more. I think we have evaluated them, but we are just adding the last one. Oh, okay, but actually 5 and 6, they are exactly the same, because we forgot to take the inverse Fourier transform. So in the Fourier domain, this ut, we modify this a little bit, but now let's get the u real. Okay, so that's why 5 and 6, they are not different, but let's evaluate. Now we take the Fourier transform of the modified Fourier domain, And then let's plot this, but let's plot this one as figure 7. And here we get, we might get, okay, so here we see a much different function. And it looks like we're changing this quite a lot, okay? So we were changing considerably. And the major reason here is that we are changing the signal which is in the center. Or with what we say in the center, we're changing the signal in the low frequency terms. So the original data, it was like this, okay? And this one, the frequency component is relatively low. Now, when we have this data which is in the k space, so this is equal to t, this is k, and this is the function u, and this is ut. This ut is the Fourier transform of u, and what we are doing, we're just erasing one data point right here. Okay? I'm sure you can pin to my camera, and if you pin to my camera, I believe you can see these. So that we just remove one more data point, but we remove it again right in the center. So clearing out these, the function, it will in principle, it will change like this. And it looks like it is greatly affected by removing specific data points. The reason for this is that this has no noise, and also we can say that this is a smooth function. The major contribution is in the zero domain. But one thing that we can remind each other is this aspect, that whenever we take the Fourier transform, we get the zero here, and then here we get plus k max, the maximum value in the k, minus k max. So this is always the case. And after this small modification here, I believe now it's clear we could do a little more, how can I say it, damage here. Let's change. Let's say 12, 11, 09, 509, 508. And we can observe, just this one, we need to modify, evaluate the selection. Let's take the Fourier transform of this. Two more data points affected the graph, figure 8, and I think we won't do this one manually for a lot more values. But we just want to see actually how much we are affecting this one. And probably with this example, we can also, let's see, is it really different? It is. It looks like the amplitude here, it has dropped from 0.5 up down to 0.45, and we see some more fluctuation. So actually, now that we are seeing more fluctuations, it looks like we are keeping alive only the high frequency terms. So if we think this one in terms of the Fourier series expansions, we are keeping only the high frequency terms, and we have removed the very first few terms, which have the highest contribution. Also, because those are not modulated very much by a factor, which often looks like this. So if you remember in Fourier series expansion, often we'll have sine of nx divided sometimes n squared or over n. So as n is increasing, sine is a bounded function, which is from +1 to -1. If you keep dividing it by, as n is getting larger, the amplitude coming from those frequencies, it will be small. So again, you can see, by looking at this example, we can also remind ourselves that the low frequency terms, they are very drastically affected if we remove a few low frequency components. Okay, so I believe we can close a few figures so that we don't have to override close all. So let's not deal, and we can also clear all the data so that we don't have the zeros over there. And so let's continue like this. This is a u function in the real domain. We can plot it. This would be the ut, the line 104 here would be the signal in the evaluate selection, the signal in the transform domain. Actually, this is transform domain right away because, no, actually this is this real domain or, no, this is the time frame from -15 to +15, this is time, it's not the frequency. It's very, almost, it cannot be that, it doesn't always happen that the time and the k space, they change from the same value, from -15 to +15. And now, let's see, let's plot these two values. So as we said before, in this graph, in the very first one is a signal in real domain, the second one is in the complex domain. Let's not modify, let's not use this part for the moment. So let's leave this here, and let's try to add noise with an amplitude which we can set it at equal to 6. So adding an amplitude of 6 in, and let's see where we are adding the noise. Based on what we saw on the board, apparently we say UTN. UTN is, U is the original function in real domain, UT is a Fourier transform, and UTN is a Fourier transform with noise. And the noise is added like these complex numbers, which is the UT, plus the noise times some complex numbers. Okay, so we add here I, this is the square root of -1. So once we add this noise, you have UTN with noise added in the complex domain. We take the inverse Fourier transform, you get evaluate selection, we get UN, and this is what we obtain in the end. Okay, so this is the diminished signal, which is, this is in the real domain. If you see the x-axis here, this is the real, the very first one is a real domain, -15 to +15. Here you see from -60 to +60, and here we get again -15 to +15. And actually, if we follow that algorithm or procedure that we mentioned before, this is UTN. In fact, right here, after we take the inverse Fourier transform, this would be, well, we can call this one U, the signal, Fourier transform with T, with noise, and then we can put here IFT, inverse Fourier transform of. So this is how we can denote actually all the steps. But in principle, this, I think the rest is clear. We can just modify all the signal by changing also the level of noise. So here we have set equal to 6, and we have yes, the amplitudes has gone from 1 to 1.5, and so on. So okay, so this is what we see here with regard to this exercise. Now let's see what we can do next. We can follow wait a second. So okay, so we added the noise, and we just did the description of how we add the noise. Now we can also see how we can remove this random noise, but how we can remove it both in the real domain and in the complex domain. So we can assume that we have a function which is noise inverse. So on the board, we wrote this one as noise inverse, which in principle would be, this simply means averaging. Okay, so if you are in a lab and you are taking a lot of data and the noise is too high, the simplest thing that you can do is that if you have the data in an Excel sheet, you can just average for each data point. You take the average of that one with 2 data points before it and 2 data points after it, which means that you have a kernel of 5 elements, okay? Or if you can also take the average of specific data points with 3 data points before it and 3 after, that means that you're going to have a kernel of 7 by 1, and you report that, and that is a very good way to remove very high frequency terms, okay? So averaging with a neighboring point. But now, so now this averaging function, which can be used both in complex and in the real domain, is the noise inverse function, which we wrote it on the board. Now let's see what this example provides for us. Yeah, so let's clear out some of the. I think we did this. We can see here white noise. Let's see what we get here. So again, the same task is that we define the x-axis, the real domain. We define it well. Apparently we have 512 data points again. And then we have to define also the wave number or the frequency component. So for some students that come from the electronics engineering, I believe you might have seen this wave number, which is equal to 2 pi over lambda, which has units of inverse meters or inverse seconds, which would be hertz or inverse meters. So once we generate this, we have also the ks, which is the shifted version of these. And then we define the real function in the real domain. Okay, ut, we take the Fourier transform of this function, and then let's see how these two look like. It's going to be something similar to what we saw before a while, I believe. So again, we see that the real domain range from -15 to +15, we get from -60 to +60, and this is, we can check actually, so this is -15, 60. We can also change for a moment, we can set here 40. So we have 15 and 60. We're talking about just about and let's run this again. The first one I got -20 to 50. -20 to 50. Or 20 and 50. In fact, this is not the best way to check this. The best way would be actually to check the width, the half width. How do you call this one? FWH map. At the half full width at half amplitude. Okay, so full width at half maximum. This is what we should be looking for, and I think you can also experiment a couple of more times. You see here 50, which we're changing the real axis. Evaluate the selection, but the 50 is changing from -25 to 40. So it looks like as one of the domains, or as the real domain is decreasing, the complex domain is increasing. And regarding this, we have a principle, which is the Heisenberg principle, which what it states that any delta x times delta k is larger or equal than a constant. So this principle is always obvious, and it is very obvious, especially for the fact that we always have errors because we are using discrete data points, okay? Which means that delta x is different from 0, or it's large, it's not negligible. If we have an infinite number of data points where we don't have discreteness anymore, we might observe some interesting features of these Heisenberg principles. So, and this one, it is more clearly reflected if we look at the width of these two Gaussians, okay? So let's leave now this analysis of how the width of the x and y axis change, but this is essential. We have to know this one. And so what we made so far is that we have the signal in a real domain, we got also the signal in the complex domain. Apparently we can add some some noise level, and we assign a vector full of zeros, and let's have an averaging of the data set up to 300 values. And let's see what we have here. We have here the UT, it was the Fourier transform of the signal. UTN, it is with noise. So we add this noise plus random numbers plus I times other random numbers. So this is really adding a phase and amplitude in the complex domain. And then we do the noise inverse function. So we can consider this one inverse noise. Okay, like if we think of these like operators. Okay, inverse function, inverse noise. And we find the average after each new value, and then we just plot it. So I think up to this part, we did this part. So let's see what. Okay, well, this is what. So this noise, this had an amplitude of 100. So this is very diminishing factor. So let's use here maybe 30, and we have here a shorter time. Okay, so still the noise is pretty high, but if we average a little more, we can completely attenuate the noise. But let's see what have we plotted here. We have plotted here the, let me see, we have plotted the complex domain graph. And let's add here another 0. We make time shorter. Okay. So this is the complex domain because it's also obvious from the values in the range of the x-axis, which is from -60 to +60. We could also plot the following. So we have here average 2 and okay, yes, average 2, which is averaged out. We can also try this one for a moment. We can say that we had the u, which was Fourier transform, then added noise in that domain, and we say IFT, inverse Fourier transform. So what we do here, we're just coming back to the real domain, and this would be equal to IFT, inverse Fourier transform of average 2. So let's see what we can get here. Then so here we can plot t, but wait a second, I guess we have t, so t will always be the same. And here we are going to plot oh, no. Wait, I think it's best if we did this here. Should be time, because actually here, this Ks absolute of FFT of shift of UT, this is the red signal, which is a signal without the noise. Okay, so we have plotted two signals on top of each other, or yes, on top of each other. And here, let's plot here time and the signal, which is Fourier transformed with noise in the Fourier domain, inverse Fourier transform to get it back to the real domain. But then here, I guess we have to plot some other function. We have to plot here just u. And okay, u is still there. Okay, this is IFFT. Okay, so why couldn't we see this? This is the original signal is clear, and okay, absolute value. Let's say the absolute value here, and let's try this again. Wait a second. So we need to do the shifting of these values of t then. The shifting, yes. So when we go to the real domain, this is Okay, so apparently for the real domain, the amplitude is pretty large, and maybe actually let's observe from where did this value come from. Evaluate selection. So initially the amplitude is around 100. So this keeps decreasing. Now it's 12, 10, etc. Okay. So we can even do this here. Anyway, so it looks like the real domain it was from minus 15 to plus 15. And then we do this one, let's say minus 1 to 10. Okay, yeah, so what we see here, we see that we can, to clean the image from the noise, we can follow several different paths. So this one, it's getting closer and closer to the real value. It remains a question of how long we need to average this out. I think this is over. Busy, it's not over yet. It is still decreasing. Okay, it's still busy. Apparently, yeah, we put too much time over there. But the amplitude, it could be good if we do also here plot. It's below the 4. So another thing that we could have removed the noise from this signal, it could be the following. I can write it in here. So we have the signal U. We could get the Fourier transform UT. Then we get the noise in the complex domain, and then we take the UTN with noise with inverse Fourier transform, which means that now we are in the real domain, and then we do everything here. Okay, so we could also follow this path. So removing the noise, we could also follow this one. So signal, Fourier transform. So actually this is, let's call this one, this is real domain. This is complex domain, UTN. This is complex domain with noise. This is now real domain with noise, okay, because we do the Fourier transform. And then we average in the real domain, average in the real domain. Okay, so we could do this. Now, what we did in this example, we got this far. I think we added the noise here, and wait a second. So we did this. So we got the signal in real domain. We took the Fourier transform. We added the noise, and then we did the noise inverse. Let me do this like noise inverse. We apply the noise inverse here in the complex domain, in the Fourier domain, and then. So wait a second. So this is complex, yes. Yes, it's clear. Then we take the noise inverse, which means that now we have still UT function transform with noise inverse. We are still in the complex domain, and then we can apply Fourier transform of this signal. So I can write now this like this: Fourier transform of whatever this variable is here. So now this is real domain. Okay, so the objective is so we can follow a few different paths, and it's good to write them down because they can even become intuitive. And by the way, this is up to 2. Let's close this one. So I hope we understand also this part here, and let's give a try by and let's put here the amplitude not 10. Let's put this 3. Oh, sorry, I didn't pick up the M. Yeah, thanks again. I thought I was getting it. No. Statement. Yeah. What would be an interesting exercise, so as this one averages out, what is an interesting exercise is the following. What could be the error between, if we start like this, we start from the same point, and then what happened around here is that we move around in the complex domain, we add the noise over there, we clean in there, and then we come back to the real domain, versus we follow this other path. And it would be interesting to check what is the difference between this function here, okay, the final result, and this function here. So we just do a subtraction, and we can see actually what is the amplitude of these. Okay, so it looks like, yes, we move. This might take a few more steps. The main objective is how to make this zero and to have as smooth as possible function around here. But actually, what is something which we are penalizing ourselves too much is that this amplitude is huge. So with such a high amplitude, now this is still busy. Yeah, apparently 3,000 steps, or maybe we need to remove. Wait a second, so this is the noise here. Busy. Of course, it will pop up again. And meanwhile, I want to ask you, were you able to find the textbook of this course? So I'm asking about actually this textbook. So this one which we suggested that, or which is going to be the text for our course. I hope you can find it and you can consult, because it's really a very good book. Wait a second, okay. Where can I stop this one? I cannot. Okay. Anyway, okay, so we can. Okay, I was wondering if we could check actually what the effect would be if we are dealing with a smaller noise. And we'll never see this example again. Okay, so it looks like the very high amplitude had an expected negative effect. It's over. Okay, fine. So let's go. So I would suggest you to go over especially these two different paths and see if you find any difference. And let's see what we have next, which could be. So here we see another example. Apparently, we have added noise in the complex domain. And these codes, you have them, so you can download them from Google Classroom. and you can experiment them around. So what is this other one about? Added in the frequency domain. So we keep, this is something similar, remove noise in the Fourier domain. I think we took the average here, yes. Where is this editor? So again, we have again a hyperbolic function, and the real domain and the complex domain, they are the Fourier transform and the original one, they are the same, not the same as what we saw before. And now we can add the noise with an amplitude of 11. Let's make this a little smaller noise. We have the UT, okay, here we are. Fourier transform plus the, whenever we see this complex number, we understand what, in which domain we are adding it. And it looks like the third figure is going to be exactly the same like the second one, but modified with the noise levels. And now this function here, or this function that we see here, we can take the inverse Fourier transform. And let's see what we get. So, as expected, we start with this function, which is no noise. This is the real domain. So let's have on the right side, let's consider we have the real domain. Then we go to the complex domain. We can track this down also by the values of the x-axis. This graph and this graph, they are both from minus 15 to plus 15, and here this is minus 60 to plus 60. So this is the complex domain. So we move from here to here with Fourier transform. Then here we apply the noise function or the noise operator to come from the second to the third. And from here, we move this way with inverse Fourier transform. And this is the path that we have followed. Okay, we have followed a clockwise path between these data sets, which are shown here on the monitor. And as a result, we observe this huge noise added to the signal in the original domain. Now, what we said so far, we mentioned that we can make things better by cleaning them, by applying the inverse noise function either here or here. Okay, they can cover the task. And the thing is that it's not always that we are trying to remove the noise by applying. So far, what we are doing applying box filters, okay, or we are applying Gaussian filters, because a Gaussian filter is very similar to a box filter. And what box filter is about is that we are multiplying with a kernel 1, 1, 1, 3 data points. So let's say that we have 3 subsequent data points which are next to each other. We convolve them with a kernel which is 1, 1, 1, which means that we're just adding them and dividing them by 3. So we're taking the average. The Gaussian kernel, it could be 3 by 1, but it's more like a wavy thing, which is coming down, which in principle, it could be some values like 0.1, 0.7, and 0.1 again. So this is what the Gaussian filter can look like. And our objective is not always to apply this linear filters, because box filters and Gaussian filters, they are linear ones, they are not nonlinear. So they remove high frequency terms. But we are going to see also cases how we can apply a notch filter. With a notch filter, that means that we can erase a specific frequency. So for example, if we see this figure here, we can try to filter out these frequencies that are from 20 to 40. So this range here from 20 to 40, we can filter it out by applying a notch filter. Notch filters are traditionally filters that are very narrow. Okay, so you clear out a specific frequency. So you remove the frequency, let's say 731 hertz plus minus 3. This is a notch filter. You could also have a notch filter which is 773 hertz plus minus 10. Okay, but this would be clearing out or blackening out, which means that we zero this completely. Okay, so all of these high terms between 24 and 40, they become zero. So these are all possible operations that we can follow. For example, let's assume for a moment that we set. Wait a second. So let's set k equal to 40. Let's set here k0 equal to 40, and let's generate a filter which is centered at 40 with a width which is 0.51. So let's generate this filter, evaluate selection. Sorry. And then we do here, we say ut, function u, Fourier transform with noise filtered is equal to this expression. And we evaluate the selection. We have this, okay, this is ut and f. We are in the complex domain. So we have to plot something which looks like figure 3. Let's plot here figure 5 here. Let's use, okay, let's call this one figure 5 that plots ks and ut and f. Wait a second. Why did this do it like this? 69. 69. So we did a mistake here. Oh, okay. We did no mistake actually. Can you figure out what happened here? So we just preserved. So when we set k0 is equal to, when we set k0 is equal to 40, we are putting the notch filter at minus 40 because the Gaussian equation is exponential of x minus x0 squared divided by 2 sigma squared. This is what we obtain, and apparently we cleared out completely these high amplitudes. So the highest amplitude, the highest component of the original signal is in the frequency domain right around 0. But now we set it equal to 0, and now so this is cleared out. And we can take the inverse Fourier transform of this signal to see what has remained. To do that, so we have to apply, we have ut and f, we have to apply this u1. So let's go now from this figure 5, let's obtain the Fourier transform to go to the real domain, evaluate selection. We say figure, let's call this one figure 6, plot t, u and f. Okay. Okay, this is what we see. So now, this is the original one. This is the first level when we had this is 5. This remains here. This is the equivalent of this. And these are equivalents, these at the bottom, they are equivalents of each other. So, but we can see that this remains that we see here in this graph, the amplitude is very small, which means that this specific frequency, which is located here at k equal to 40, and this is pretty narrow. If you see this one, this is pretty narrow. So we are keeping alive only this specific frequency. This is like a notch filter, and this is what we observe here. So in all of these locations, we observe that actually, why is the amplitude a little higher here? Can we distinguish it? Can we figure this out? Probably not. Okay. Because around 0 we have high, and we have a very nice feature which looks like this. Now, we could also define a filter which could be as follows. So So let's do it like this again. We don't want to close everything, so we can have the graphs, but we could clear all. And we want to keep these graphs as a reference. We generate the real domain x-axis and the complex domain x-axis. And we plot, actually we don't need to plot these because most probably they're going to be the same. So figure 1 and 2, let's keep it there. Noise level, we set it at 7. Then, okay, we don't have this value, so we need to generate it again. Evaluate selection. Figure 3, I think we have this figure 3 already, but we can plot it again. Let's see, it should be the exact same thing as before. Yes, it did not change at all. And now we have the signal, which would be the, okay, this figure we also have it, but let's calculate it because we need to write it. And now let's have here undefined functional variable UTN. What did we do here? Or maybe we skipped something, okay. Evaluate selection. Generate the x-axis for both domains. Then let's do everything. Actually, let's do this. I mean, we are going to plot the same graphs again. Figure 4, let's have the figure 4. Figure 1 and 2, they are already there, but let's have them like this. Okay, we knew what they looked like. So figure 3 and 4. And now let's have this, our filter. Actually, this is too far, but let's keep it still there. Evaluate selection. And then, now let's make a filter, but the filter should have a very large bandwidth. For the filter to have a very large bandwidth, we could change, so we know that in the numerator, in the denominator, here we should have a large number. So this is over 2 sigma square, 2 sigma square. Let's put here, I don't know, let's put here 20, for example. Evaluate selection. We filter, sorry, we filter the, okay, we filter this one, this graph, this figure 3, we filter it with this filter, which is centered at 20, but a very large bandwidth. And let's see what we get for figure, let's call this one figure 51. So figure 51, we have to compare it with figure 5, evaluate selection. Okay, so apparently we could have given a broader bandwidth. So figure 5, it was like this, now this is 51. Now we generate, now we go to the other domain, to the real domain. We do figure 61, and let's plot this again. Let's see if we get anything closer to the, so this is figure 61. We still, it doesn't represent much. So this is the difference between 6 and 61 here. Okay, and by the way, this signal which we had here, and let's remove this from the comment, we need to use this one, and we have here plot, and this 20, actually this, let's calculate it ourselves. In order to have the filter centered at 40, and also preserve some of the lowest frequency, the sigma of this filter should be 20 plus 20, 40. So this is 40. Actually, here, when you set this 20, this 20 is equal, because we divide by 2 times sigma times sigma. This is how, and because the exponential function, I think we know that the Gaussian function, which is, this is not a pure Gaussian, but it looks like that, is equal to, no, actually, Sorry, the filter is a Gaussian. I apologize. So Gaussian is exponential to the power minus x minus x0 divided by 2 sigma squared. So if this 2 sigma squared, if this was equal to 20 before, okay, so this 2 times sigma, this is equal to 20. That means that sigma itself is equal to 3. 3 doing that. But sigma apparently was equal to 3 in the previous case, and we moved plus minus 3 around. But now we want to center it here, but we have some low frequencies still alive. We can make them, the sigma would be 20 plus 20, would be 40. This is the order of 40. It's not going to be precisely 40. Then 40 times 40 times 2, because it will be 2 sigma squared. This is equal to 16. 0 times 2, it would be 3200. So then this filter, we can put here 3200. And then all we need to do is we need to do this here and run this value selection. This is 51, but as you can see here, this was, so 1, let's try to separate these. 1 was the original signal, no noise, that's good, it was here. Then this was the Fourier transform of this, the domain is from minus 50 to plus 50. Figure 3, it was when we added the noise, it's here. Figure 4 is we removed the noise, and we didn't remove the noise, we just came back from right to left of the monitor. And here, we just multiply this figure 3, we multiply with a filter which was centered at 40, but wait, no, there's something wrong, no. This is because the range here is from minus 15 to plus 15. So then we bring this figure 5, this is this way. Okay, we have to correct this. So actually, this one, we said that this was centered at 40, but is wide enough to keep this alive. You see that we still have this amplitude. So which is used to be 60. It looks like the amplitude of this huge Gaussian is equal to it really comes up to this point. So we have some higher values in this side. So we have filtered out these frequencies here, anyways. But then finally, it looks like we have a better reconstruction rate when we have a wider filter or notch filter in the frequency domain. Okay. Now we filtered here with a filter which was centered at 40. If we filter with a filter which is centered at 0, let's see what we get. So let's set this 0, and but actually, oh, it will be interesting if we use it 0 and we keep the bandwidth 3200. Okay, let's do that. And let's go like this. Which line were we? I think we are here, line 234. Okay. Create the function noise level is this one. We use a filter centered at 0, but it's unrealistic to use a filter centered at 0 and have a bandwidth of 40, okay, which is line 269. Let's see what we get. So we plot everything from scratch. And 61, this is the real domain because it's going from minus 15 to... So it's 51, it's here. So this is not affected at all. This is figure 4, real domain, the signal with noise. This was in complex domain, and so on, okay? Now, it doesn't make sense to filter the high frequency terms by preserving only the lowest ones with such a huge bandwidth. So we are centering here at 0, but this goes 40 units around. So this still keeps a lot of high frequencies. Nu kur se kemi here gjë noise me këtë këtu, but we can decrease this a little further. Let's make this one 0.2 or 0.1. Okay, let's use a filter centered at K0 equal to 0 with a very or relative narrow bandwidth. Let's go to line 234. I'm almost sure that most of us know what we are going to get. Okay, so well, this is huge. Wait a second. This is very wide. This is 51. This is the real domain with noise. This is complex domain with noise. And this is the complex domain with no noise. So we go step by step. Left, right, that means from real to complex. So no noise Fourier domain. Then here, with noise Fourier domain, here with noise in real domain. But then we do the filtering down here, and we preserve very low frequency. So this is what we observe. Now, this is almost non-realistic, okay? Because we see that this signal here is wider than the original one. So apparently, we have even these low frequencies, okay? They are centered at 0, but those also have some bandwidth, okay? So this one has some bandwidth that it should preserve. We should not be so harsh on this component, but it looks like we can predict or we can experimentally determine what is the bandwidth of. So we're talking about the bandwidth or the frequency component of this original signal, okay? Whichever way this is changing, this is not like a sine. And how did we make this one? We made this one. So what is the bandwidth here in real domain? This is plus minus 2. If you look at the width here at the middle of this amplitude, it's plus minus 2, then this has jumped to plus minus 5. This is what we see here. From plus minus, maybe plus minus 1 probably, plus minus 5. And this was all done because we filtered very harsh. But what is interesting is that we have no noise. So all the high frequency terms, all the noise is gone. So this is how bad it was, but we could clean it out with notch filters. And notch filters actually, a filter which is narrow but centered at 0 is not commonly called notch filter, because notch filters are designed to clear out something which is different from 0 in principle. This would be just a very good low-pass filter. Centered at 0, it makes it notch. We can still use it, but yeah. So now, what else we can do here? Okay, so more or less, this is how we can manipulate all of these signals, including also the way how to filter the signal. We can experiment similarly at home. Now, remove noise by averaging. Let's see what this is. This is another example how to add noise. Apparently, you can guess where we are adding the noise once you see this I here, and we average out in the same domain. And now, what we can do is that we can look at another example, which can be provided here, and let's close all the figures and let's clear some of those. Clear all. Okay, so let's say that before we go to the next example, we want to talk about. Here, please let me stop again. So let's say, so far we're doing Fourier transform, okay? But Fourier transform, what it's doing is that whenever we take the, so let's say we have a signal that is changing from 1 to 2 to 3 to 4, okay? And this has a special behavior. If we take the Fourier transform from this signal, we lose all the information. So let's call this one t, time, and let's call this one k. Actually, the k, we should plot this one, this is not correct. Let's put the 0. Let's put the 0 here. We should know this. This is the k. And this signal has what frequency components would this have? So, what is the Fourier transform of this signal? This is a good question. If it is a pure Fourier transform, you can always say, okay, it has no frequency terms, so you can always draw this, okay, with a certain bandwidth, and this is how it will. So you can always draw something like this if you don't see any crazy noise on top of it. But now, when we take the Fourier transform on this whole integral, I think it is good. So when we do this one with a numerical technique, we are using a discrete method. Okay? We have discretized the model. So we are using discrete modeling. But to understand what we are going to talk right now, it's always good to make a comparison with the analytical expression. So the discrete one, this is numerical method approach, okay? Where integrals and derivatives, they are written carefully with the delta x's, with whatever we learn in the first few weeks of calculus. So this is the numerical approach. But in principle, the f of k, this is written analytically as follows. We integrate from minus infinity to plus infinity of any function f of time. Let's write this omega, because I think some of us might have seen this one this way. And we have the function, which is this. Let's call this one f omega. And let's call this omega. This would be f of t times a kernel. So whenever we do a change between domains, we multiply by a kernel. A kernel is a function which links two different domains, and in this case, this is minus I omega t, okay, times dt. So we integrate over the whole time, but we know the following. If we are going to integrate from minus infinity to plus infinity, which means that we lose all the information about the time, okay? We don't know anything about time. We erase that information completely, because we know that if we put the limits, what will be the answer? The answer will be just a function of time alone, okay? So similarly, when we come backwards, so this is the Fourier transform, the inverse Fourier transform will be the following. F of t would be equal to the integral from minus infinity to plus infinity of f of omega times e to the power I omega t d omega. So now, when we integrate here, these omegas, they will go away. So we are not going to see them because we are integrating over those, will remain with only a function of time. Now, it is, there is a Gabor developed a technique which he called short window Fourier transform. Short window Fourier transform. Short window, he said that I'm not going to integrate this one from minus infinity to plus infinity. And by the way, since we know very well when we integrate an expression, we know the analytical expression, sorry, the analytical definition, it's not that we're going to integrate from minus infinity to plus infinity. In this case, we're going to integrate from 0 to 4. Okay? But it's good to remind ourselves of how this is, and also to understand that really, once we integrate, all of these terms will get lost, these time functions. And now, what Gabor developed, he said that when you take the Fourier transform, we can multiply the given function with a window, which is the window is going to be 0 to 1. So we can multiply it like this, 0 to 1, and take the Fourier transform of this remaining function, of only this component. Then what happens is the following. So let's assume that we have a domain where we have here time, and here we have the omega. Now, initially, what we did so far, where we did the complete Fourier transform, we did the following. We did something like this, which means that in this domain, we have all the information, so we have all the information in time domain, and the width here, the resolution here, so let's call this one delta omega. This is small, but if we integrate, if we multiply the original data with a gate function, which is, let's say, initially is this one, and later it's going to be this other one, okay? So this is 0 afterwards. What we can do is the following. We can divide the delta t by 2, so we can call this one, so delta t, what is delta t here? Is the whole time, from 0 to 4. But applying a short linear Fourier transform, we get here delta t over 2, and here delta t over 2, and here we get 2 delta omega. Assuming that delta omega, we are assigning the initial bandwidth that we obtain when we integrate over the whole term. So we can go on like this, and then what we can do further is that we can cut this a little more, so we can separate, we can do Fourier transform from the real domain into the context domain by integrating over a quarter of the whole range. So this would be delta t over 4, delta t over 4, and here we can say that this is going to be 4 delta omega. Okay? So in principle, we can say that, and we can call this one the area, we can say it like this, area in phase space. Is constant. Now, it is very intuitive to calling these this phase space, because some of you, especially the electronics engineers, it is very important for you to understand this one. For computer engineering students, only if they are going to deal with a very specific problem. If anyone is, let's say, if in the future, anyone from computer engineering students go into some quantum computing, I mean, you should understand this very well. And to understand this, you need to read like two or three books, okay, huge books, because the concepts of phase space, they're not very difficult, but they are fundamental. And with the phase space, we call what is the area in phase space. The area in phase space is this area here. Okay? And this area is never changing. Okay? So you can say here delta t over 4 times delta omega, it's always the same. So there is something that phase space, Hapsira Fazore, show fundamentale. I don't want to completely move out of the text of what we are doing here in this course, but I believe in 5 minutes we can provide some information which has also some, it can serve your intuition later on. What we mean with phase space, meanwhile, can someone just talk? Am dați de kush somos generat gjithë në gjumë, nuk është vetëm kjo arsye, por thjesht duhet pa edhe apo dëgjoni. Po,
profesor. Ju profesor, ju.
Okej, jeni po mirë, a keni marrë bukë pak, apo hani bukë, a keni marrë tasin përpara. Shiko, if the internet fluctuates, I might be disconnected, and I'm talking here for hours with you, ose ndajherë unë zërni mikrofon e kësaj speakerit unë edhe s'marr vesh edhe kur kundërshtoni. But okay, we are here. So now that we shook up a little bit, I just want to say in a very short 2 to 3 minutes, I want to say a few words about this concept in phase space. This is the best place to talk about this because phase space, it deals with Fourier transforms, okay? And other than the mathematical tools that we use, there is also this, which we're going to talk right now. And this phase space, this has an area which is equal to this side times this side. Right? This is, you can think that this is the smallest possible, the smallest area that we can constitute here. And this, the smallest area is the smallest constant, which in principle, so here we have delta t times delta omega, it comes from the Heisenberg principle. We wrote this one a few minutes ago, so here we can assume that each time delta t times delta omega, this is something larger than some constant. This constant, it is something like 6 times 10 to the power minus 36. You might say, why should I care? Electronics engineering, you might have seen that if you have a photon, which you can measure with a detector, the photon can have a frequency of, let's say, 3 gigahertz. 3 gigahertz. 3 gigahertz means 3 times 10 to the power 9 hertz. And this is the frequency f. You multiply this one with the h, which is the Heisenberg constant. You get the energy, which is the energy of the photon, okay? So 3 times 10 to the power 9, you multiply with 10 to the power minus 36. So we get some joule, but how much joule? You get 10 to the power minus 26 joule, okay? 10 to the power minus 26 joule, sorry, 10 to the power minus 26 joule. This is how, and you can convert this joule in electron volt. What is an electron? An electron volt, you divide this one by 10 to the power minus 19, which is the charge of the electron, and you get something like 10 to the power minus 7 electron volt. Okay, so you can get these numbers, but you have the energy of the photons. So it's not something that you never use. Okay? If somebody asks you, for example, find how much pressure is the sun applying to our bodies, this is what we do. You get the H factor, you get the frequency of the photon that is coming, and you can find how much the momentum of the photon is exerting on our bodies. It's very small, but it is different from zero. So this is the smallest quantity, and this smallest quantity in the phase space, pra vëllimi më I vogël I mundshëm në hapësirën fazore është kaq, është 10 minus 36. Dhe gjatësia e valës që korespondon për këtë është një gjatësi vale më e vogël e mundshme, gjatësia e plankut, është 10 minus 34 metra. Pra është një vallësi goxha e vogël. Tani kjo pjesa është, this part it relates mostly probably with half of the class, unless the other half does not go to quantum computing later on. Then you're going to need this one. But then, other than this, we want to have a look at this one. What is the phase space? What is the unit of the phase space? The unit of phase space is the most important unit, and we'll try to clarify why is this so. Wait a second. So, phase space, what is the unit? It is time, it is second, times what is omega. This is in fact second, this is not hertz, but this is radian, because it's omega, it's how do you call this one? Radian 2 pi f divided by hertz, by second. But wait a second, so we can e to the power minus kx, e to the power minus I omega t. I think you have seen these quantities, and this k is 2 pi over lambda. So this is the unit. I can prove this one, but for now we can assume that this is the unit of the area. This is not meter square, but this is the unit of this quantity times this other quantity. And this kilogram times meter per second, this is mass times velocity, okay? And this is distance, x. Now, what does this look like? This looks like the angular momentum, which is like r cross t. Okay, this has the unit of L. Now, why is this such an important quantity? Because this can help us to understand some symmetries. I'm going to give just a couple of symmetries. One symmetry is space is isotropic. What I'm saying right now, I'll be done in 2 minutes. Okay, so let's not get very afraid. So space is isotropic. So it does not matter if you turn on the laser this way or this way. Since the space is isotropic, that means that we have some conservation laws. So space is isotropic. So a symmetry in X or isotropicity in X, this concludes that P is conserved. Okay? So the conservation of linear momentum that you might have seen in physics, it is because space is isotropic. Similarly, an experiment done at time 1 second is the same experiment with time 2 seconds. So if you do the experiment after 1 hour, we are going to get the same expressions. And because of this, we have another conservation law in nature, which is the conservation of energy. Okay? And what is interesting is that if we have a symmetry here and a quantity is conserved, we always get the following. We get x times p, and here we have p times energy. The units of this is also the same. So the unit here is also h. This is also h. And this expression here, delta t times delta omega, this is in fact, we can say the following. So here we have delta t times delta e. This is equal to this constant. And delta x times delta p, this is also the same constant. So now this p, this is delta x times h times delta k. In principle, this is how p is expressed as a function of h. And this is also h, but this is 2 pi over lambda, that's k. The students of electronics engineering, you might remember that we have these terms for the propagation of a wave and so on. So this phase space, which here we are just observing that the smallest quantity in phase space is always constant. If we're saying delta t delta omega, then you cut this in half, you lose. So what this means in fact is the following. If the resolution in the measurement of time is 5, then the resolution in the measurement of the frequency is 1. If the resolution gets better, if you make it 5/2, then we lose the resolution here. So you can consider this one like an error. That is the error in measurement. And the error in measurement, that means that you get more and more precise in time, okay, but you lose much more information in the frequency. So similarly, we can say the following. Let's say that you care too much about the resolution in an image. So this t, this time, is not time anymore, but it's x. It's meters, or maybe micrometers. So you say that you want to construct a microscope, and this is the only case where you want a very high resolution. So you want to see two little components that are very close to each other, and you need to resolve those. If you look from too far, they look like one point, but you need a high resolution. That means that it should be something like this. Then you try to increase the resolution in time domain, but as you increase the resolution, what we are doing is that we are dividing this more and more and more, but then increasing the resolution in space, we lose information, or we lose, we decrease the resolution in the k-space. Okay? So now, this as an intuition, by understanding at least that there is a relationship between the resolution in one domain with respect to the resolution in another domain, we can find usages of these approaches in interesting areas where one of them is computational imaging. And now I want you just to bring something to remind you of something very easy, which you know this very well. Let's say, if you have a vector here, vector A, and this is vector B, what is the difference between A and B? What is the change in this vector? So A minus B, you just take the B the other way around, right? And how do we add vectors? Na vector, nga koka njëri vektor, vendosin tjetrin. Pra, kjo është minus B-ja, kjo është A-ja, pastaj bëhet A minus B, this is it. This is A minus B, okay? So similarly, if you have a vector K, K1, and another vector K2, what is K1 minus K2? Which means that, what is it? I think it's something like this, right? This is delta K. Now, this delta K is the resolution which appears here, okay? So this is, but what does this stand for? This stands for the direction of light. So let's say, for example, you might have heard this word diffraction, or we see waves. What causes a wave? You throw a stone at the bottom of the sea, and that stone, it will change slightly the direction of the water wave. Any change in the direction of a wave, it is called diffraction. And diffraction, it's a Fourier transform. So you get the original wave, you take the Fourier transform, this is a diffraction. Okay? So if you want to see patterns which look like circular features, etc., they are purely Fourier transforms or concepts that we are learning the mathematical apparatus right now. But now, so what can be diffraction? Diffraction can be, for example, we have a wave which is going like this, parallel, but this is a white light, so you send it, then you make a very small aperture, you make a very small hole, and what happens if the wave will go like this? If you put a wall, you're going to observe an intensity which goes like this, this, and so on. Now, what is this? This diffraction pattern that here we see dark. This is dark. This is also dark. So these kind of pictures, I'm sure that we have seen them a lot. But this feature that is here is in fact the Fourier transform of this point. Okay? The equation of this one. So what is this function here? This function is 0 everywhere because this is blocked, and this is 1 here. So the Fourier transform of this function is this. Okay? So the Fourier transform of the aperture, Fourier transform of the aperturas, the Venus above it, the aperture can be circular. So you can take aluminum foil, and you can you take a needle, and with this needle you just make a very small hole in the aluminum foil. Aluminum foil, it does not bend, so you can make a clear cut, and then you can do whatever with it. The most intuitive thing that you can do with an aluminum foil with a needle is that you put it there in your eye, and you approach to the monitor of your cell phone. Imagine the cell phones, they are very, very high quality. But with a small hole, what you can do is that you can see the pixels of your cell phone. It might be a little difficult, but what would be very easy is to see the pixels on your desktop. Why do you do that? How can you see the pixels? Because if you look like this, you can never see those red, green, and blue pixels on a phone. But if you restrict yourself too much, so if you decrease this, now this is delta x. So you are somewhere here. Okay? Initially, you are looking with your eye, and let's say you're having an aperture as big as your eye, is this much, okay? But then, when you use this aluminum foil with a needle, now you're jumping from here, from the diameter of our eye, we decrease it with a very small point, and now we have huge resolution in distinguishing the light coming from different sources, okay? And what can I say else regarding to this? And what does it mean for an eye? I think this is gone. What does it mean? So when you're looking with our eye, for sure, so sometimes if you want to see something good, you can even make a very small hole with your finger like this. And you look like this, you're going to see much better. So with the eye, let's assume the eye is something like this. But let's assume for a moment that the eye is an aperture like this. Let's take this cross section. And what the signal, we get the signal which is coming from here. Okay? So here we have a house, it's a huge house, it's beautiful, there are some trees, and this information is coming down this way. And what we are really doing when we are seeing with our eye, we are integrating over these little lines. Okay? So we are integrating the intensity times delta x, or delta y, let's call this delta y. So, if we make a very small hole, we can produce very high spatial resolution. We are jumping immediately from here to here. So now, with these examples of phase space and understanding of what this really means, with very practical application of making you very good observer, just by implementing the possibility of having a pinhole, which you can produce it very cheaply with an aluminum foil and with a needle. This is something which you can all experiment, but this is all coming from the principles that the phase space, the smallest area in the phase space, the moment you restrict yourself here, you get much more details in here. Okay? So from here, it looks like if we bend the light too much, let's say you have Originally, the light is coming this way, and you have a very small pinhole, and so this is K0. Initially, the light was intending to go in a straight line. Because of this aperture, we get this. This employs that we have a delta K in this direction. Sorry, this is delta K. And you can see how delta K is here, right? And the final sentence could be this, that losing resolution in one domain increases the resolution in the other domain. But sometimes what we can consider here like the error in measurement. So you might also think the following. I think this is also a little bit intuitive. Very often you can say, what is x? X is x0 plus minus delta x. Okay? And you say, what is k? K is equal to k0 plus minus delta k. So this delta k is that we plot here. You can also assume like the error in measurement or resolution, which is almost the same thing. Okay, but what I find it very impressive personally is the idea that these patterns that we see, that we might have seen this very often. So you take this aluminum foil with, you can do this at home. You take this aluminum foil and then make a hole, turn on the cell phone light, turn off the light in your room, and you send the light, and you're going to see this diffraction pattern on the dark wall of your room. Okay, this is how you can do it. And another thing that you can do is also the following. You can measure the thickness of the hair. So you pick one hair like this, and you take a laser pointer, a laser. You can buy it very cheap for €5. You shoot a laser to your hair, and what you are going to see on the other side is the Fourier transform of a line. Okay, so you have a line, and you are taking the Fourier transform because it is the same thing for Fourier transform. This versus so. Pra, ne mund kemi një burim drite që mund të jetë bllokuar drita komplet, so we can have a source of light, which would be this pen, and everything is dark, and this is going to produce a Fourier transform on the wall. This is equivalent to having light everywhere and having a barrier like a hair. So you take a hair, you put in front of the laser, you see the Fourier transform over there. What is equivalent to this? And you are blocking it, right? You are blocking the light with a hair. What is the opposite? The opposite is having light dark everywhere, and you just scratch something as thick as a hair. How can you do that? You take a piece of glass, you burn fire, you make a dark layer on top of it, and then you scratch with a needle. Now this is the inverse of what the hair did. Okay, and then on the wall you're going to see the same diffraction pattern or the same Fourier transform of a line. So the Fourier transform of a line, it's going to look like this. You want to see, you want to have a bright spot, darker, bright, bright. So let's make this bigger, okay, like this, like this, like this. So this is what happens, okay? So the line, anyway, I think we gave the examples here. So now, with all of this discussion, all we wanted to explain was the following: the Gabor transform. And the Gabor transform, this is equivalent to short window Fourier transform. Okay, how does it do it? It is taking the Fourier transform by also remembering from where we got this frequency component. So if x is going from 0 to 5, it's saying that, okay, I'm going to take the Fourier components, I'm going to write down all the frequencies that are in the first quarter, and I'm going to write them down. Then I move to the second quarter, I write the frequency components, I record them, I write them down. I go to the third quarter, I do the same, fourth quarter, I do the same, and this is defined as short window Fourier transform or Gabor transform. And it's not as easy as we can, not easy, it's not as useless as what we might skip. It is very fundamental. for several arguments that we try to construct or we try to prove in the last 10 to 15 minutes. Okay. So yeah. Now the Gauber transform. I think we can provide examples, but we can leave them for the next session. And meanwhile, we can also have the chance to go for you to look at the book once again. So which is this, and I think I'm going to present now. Okay, we're looking at the camera. So you can find this book because it's really a good one. But probably this discussion that we have right now, you cannot find it in books that deal with data-driven modeling and scientific computation. But you can find this kind of information mostly in textbooks that deal with optics or with whatever the engineers in waveguide optics carefully do or always do. Now, do you have any question for what we covered so far? I can also add the following. The textbook is really a good one. And it has also it provides also the analytical expressions of what is a Fourier transform and what is a Gauber transform. Now, we can work this out also on the board. And when we write this on the board, this will include several integrals, which might be a little confusing if you are following online. If you are in the same class, you can really correct me when I do a mistake. But now, if I do a mistake on the board while I'm interviewing something, it takes you some time to turn on your microphone from mute mode and so on. And I really like the derivation of the expressions, but it's a little odd if we follow this one online. So proving on the board, and we need to erase half of the board because the camera view angle is narrow. This makes it a little unique, or in the bad sense. So the reason I said this is that I would suggest to you to look at the textbook and see also the derivations where the analytical expressions or how you derive each step, where they are shown. Okay. So for today, for example, we did some exercises using MATLAB with filtering those signals or those data, and all of that was in 1D, one dimension. In the next future sessions, we're going to see also how we can process these in 2D, in more detail probably. But please go to the textbook, and you can find any other textbook that discusses the analytical approach, how to deal with Fourier transforms, and you're going to learn a lot. And you might always find pieces of information that we just discussed in the last half an hour. Most probably, it is hidden over there. It is not 100% exclusive. It's not that we did this in here, but this other textbook never touches or approaches to these concepts. No, it's not even possible to make it 100% exclusive. The treatment of Fourier analysis in two different textbooks of two different areas, there is always some equivalence. At least the mathematics is the same. But the intuition and the solution it provides, it's a lot. Okay, so this is all I want to talk for today.
Nëse mund të këtë Heisenberg constants.
Yes.
Constant. E pash vunare se u përmend 3 herë me Junis që ajo ka njësi që ajo ka, dhe herën e parë u përmend sikur ishte angular momentum, në ngjashëm me të.
Yes.
Angular momentum, dhe pastaj e barazuar me një njësi që ishte energji që shumëzon kohë.
Po.
Dhe pastaj u barazuar me një njësi që ishte linear momentum që shumëzon delta x. Jo, që shumëzon kohë prapë. Me thonë ishte një herë kohë e linear momentum.
So it's like this.
Oh, here's the angular momentum, like L, the one.
Momentum, this is equal to R plus P, right? So mathematically, this is R is delta x, P is P.
Ajo ndego, po me këtë dytën poshtë me delta T dhe me delta energy. Nuk po mdelshin units pak a shumë.
So let's see, that's a good question, Gendy. This question actually is very fundamental, and physicists don't even want to discuss this. Okay? So they just accept that this stance it is valid, but simply we can say the following. Let's divide, wait a second, so delta x, or let's do it like this. Let's multiply the delta t with velocity. Let's do here, delta t times velocity, okay? And let's have here delta energy divided by velocity. We didn't change anything, right?
Po, në rregull, po.
So I multiply by velocity and divide by velocity, that's good. So what is time times velocity? It is delta x. So I can write here delta x, right? What is energy divided by velocity? It's delta t.
Po, por me një faktor dysh. Do të më kenë.
Yes, that's true. But we are seeing, we are correct, but that e faktori dysh është vetëm mekanikë klasike. Nuk është në këtë domenin tjetër kuantik.
Në rregull.
Yeah, so that one, it goes away, and we can, this is a very fundamental question, okay? This is a very important one, but in principle, I think we remember this one, that energy is 1/2 mv squared, right? Linear momentum is mv, and actually, a better definition here, not definition, how can I say this one? Let me, if we think of these like derivatives, so for example, delta E, we can write the following. Delta P is equal to what? Delta E over delta V. Right? Now you don't have 1/2. Essentially, the derivative of the energy, so I'm writing this, derivative of energy with respect to velocity is what? What is 1/2 mv squared derivative sign met dv?
MV.
Okay, so we get this, right? So when we write it like this, actually maybe I can write it like this better. Okay? Then you don't have that 1/2. That's one excuse that I can provide. But in quantum physics, things that they don't have this 1/2. For example, the photons have an energy. So energy for a photon is hf. A constant times the frequency. The linear momentum P is equal to energy divided by the speed of light. Is this. So in electromagnetic waves, you have seen this one. We used to divide the energy of a wave by C, and we get the momentum. We just briefly mentioned this one in 1 hour. We did not do this the whole semester. But this T over C, this is equal to H times frequency over C. And what is C frequency divided by C? We know that the speed of light is equal to lambda times frequency. Okay, so we know this one. If you have any doubt, we can just check the units. Lambda meter, frequency is 1/2. So we get the units of speed. Meter times 1/2. That's the unit of speed. So what is frequency divided by C? Let's see. Frequency divided by C is equal to 1/lambda. Am I right? Yes. So here we get H over lambda, I guess. Yes. Okay. Is this correct? So we divide both sides by C. Yes. 1/lambda. We divide lambda. Yes. So if we see here, we don't see that 2. That 2 that we see in classical mechanics is not very obvious here, but it's just the ratio. Okay.
Po shumë e drejtë, derivati ishte shumë me vend.
Po, derivati ma ke pak më shumë intuit aty te puna derivatit. Po dhe kjo
Edhe diçka të funit e kjo energjia, se metin men që thotë që sa është momenti një fotonit ku na godet trupin ton, ta kanë që ne kur ta gjejmë energjinë që është në fund tabelës, F times Heisenberg, do ta pjestojmë me shpejtësinë e dritës për me gjetë momentumin?
Po gjeni. So the energy that is coming, the energy is proportional to electromagnetic field wave vector square. Yes, actually, but this one, we can discuss this. So electric field is equal to E0, e to the power ij omega t minus I kx. The energy is this amplitude squared, okay? Then we divide it by C, and we can get the, let's say the momentum. And I remember in the class in electromagnetic waves, we even did examples when we said that if we have a surface area which is 100% reflective, the momentum is 2 times larger than when the light is absorbed. We have a surface which absorbs light like this, and you have a surface which reflects light like a piece of glass, like this. This is my cell phone. The momentum transfer of a photon on this reflective surface area is 2 times more than this, because sepse shkon topi dhe kthehet mbrapsht. me tjetër shpejtësi. Pra i bie kështu futbollisti kur vjen topi me shpejtësi dhe ky e gjun direkt, momenti që godet këmbën është shumë i madh. Por nëse topi po vjen me shpejtësi dhe tjetër heq këmbën pak mbrapsh, momentum transfer shumë herë më i vogël, ulet në faktor shumë madh, okay, but thjesht ata si shembull që kur kemi bërë electromagnetic wave kemi përmendur këtë pjesën që momentum transfer, it strongly depends also whether the surface is 100% reflective or 100% absorbing, or no photons returns back. Okay.
D'accord, faleminderit.
Okay. Any other question? Okay, so if you have no more questions, we can close this session for today. I thank you for your attention. Faleminderit gjithëve. Keni fundjavën shumë afër.
Edhe ju për asa.
Faleminderit. Natën e mirë gjithëve. Natën e mirë.